Hello everyone. I am honored to present our CVPR 2026 paper, Differentiable Stroke Planning with Dual Parameterization for Efficient and High-Fidelity Painting Creation. The goal of stroke-based rendering is to recreate target images using digital brushstrokes. However, existing methods face a challenging dilemma. On one hand, traditional search-based methods rely on discrete stroke placement. This often leads to structural fragmentation and slow optimization, sometimes requiring tens of thousands of strokes. On the other hand, fully differentiable methods lack structural awareness. Because they heavily rely on pixel-level loss, they often produce visually disorganized layouts and easily trap the optimization process in local minima. To bridge this gap, our work asks a critical question. Can we achieve both the structural coherence of discrete search and the pixel-accurate refinement of continuous optimization? To address this dilemma, we introduce our macro pipeline, an iterative hybrid search and optimization framework. Unlike single-pass approaches, our framework dynamically evolves the painting through multiple refinement loops, operating in two progressive stages within each iteration. The first stage is structure-aware search. Instead of random stroke placement, we directly leverage the image gradient field. We sample seed points from areas with high reconstruction error and trace along the gradient flow. This allows us to generate geometry-aligned stroke skeletons that perfectly capture the major structural ridges of the target image. The second stage is continuous optimization. The initially searched structures are fed into a differentiable framework. Here, all stroke attributes, including shape, color, and opacity, are jointly refined via gradient descent. This iterative collaborative pipeline ensures that we preserve global structural coherence while utilizing the atom optimizer for exact, pixel-accurate fitting. The engine driving this pipeline consists of two core mechanisms on slide 3, our dual parameterization and an efficient splatting renderer. First, we establish a bidirectional mapping between two distinct representations, discrete polylines for structure perception and continuous Bézier curves for optimization. By solving a least squares problem with a closed-form solution via pseudo-inverse, the discrete polylines are seamlessly converted into differentiable Bézier curves. This dual parameterization allows gradient information from the continuous domain to flow back and guide the discrete structures, successfully helping the model escape local minima. Second, to optimize and render millions of curves efficiently, we designed a polyline splatting renderer inspired by Gaussian splatting. By approximating stroke segments as soft, anisotropic splats, we achieve massive GPU parallelization. This completely avoids the computational bottlenecks of traditional pixel-by-pixel rendering, dramatically boosting our optimization speed. We evaluated our framework on standard benchmarks like Div2K. Quantitatively, our method achieved a significant 4 to 5 dB gain in PS and R over state-of-the-art methods. In terms of efficiency, our framework requires 30% to 50% fewer strokes, which directly translates to a 40% reduction in overall optimization time. Visually, as shown on the slide, our method cleanly recovers complex textures, such as animal fur, and preserves intricate structural lines without the chaotic artifacts found in previous approaches. Our method goes beyond flat colors by regressing a height field for each stroke, simulating the physical reality of thick oil paint. This thickness-aware blending enables advanced relating effects and captures tangible surface relief. Before concluding, I would like to highlight our ablation studies. Our experiments on individual components confirm that removing either the polyline search or the Bézier optimization leads to severe texture degradation or structural chaos. Furthermore, our analysis on the iterative behavior demonstrates that our multi-stage progressive loops are essential for achieving both rapid convergence and long-term global consistency. In conclusion, our differentiable stroke planning framework, empowered by dual parameterization, sets a new standard for efficient and high-fidelity stroke-based rendering. It perfectly balances structure-aware generation with differentiable refinement, all while supporting realistic physical shading. Thank you very much for your attention. Our code and pre-trained models will be available on GitHub. I am now happy to take any questions you might have.